Hey guys, welcome back to another video. Today we're going to be talking about how binary works, okay? So, and I know that a common thing that people say about computers is, oh, computers are just zeros and ones, right? On or off. Store electricity or don't store electricity. And so the question then is how am I recording this video with just zeros and ones? How am I typing on Word with just zeros and ones? How do numbers work in binary? And so the key to uncovering this falls in looking at our base 10 system, base 10 because we have 10 fingers, 10 toes. Okay? So if we look at the number 105, for example, we all know that this is our hundreds place. This is our tens place, and this is our ones place. Or you could say that this is 10 to the 0, this is 10 to the 1, and this is 10 to the 2. And if you didn't know, whenever you, for example, with like this, the exponent for a base 10 number, or just 10, is how many zeros will follow. So obviously this is 100, this is 10, this is 1. 0 zeros, okay? So we know that we have 5 times 1, 0 times 10, and 1 times 100. So what if we want to do a smaller number? What if we want to represent 2 in binary? For example, 2 in binary. So what we could say is, we'll set up the same type of system where we'll have a bunch of zeros, and this will be something to the 0th power, this will be something to the 1st power, this will be something to the 2nd power, 3rd power, 4th power, etc. And so what you need to think about now is is odd and even numbers. We know that an odd number is written mathematically as 2n plus 1, and an even number is written as 2n. So our most obvious choice would be to use a base 2 system, because that can account for every number. And if we start it at the 0th power, then we'll account for 1. So there we go. So obviously written right here would be 0, because we're going to have 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and just as we did here where we took 100, we added 0 tens and 5 ones, I guess you could say. We're going to do the same thing here, where we add up as we move to the left, just as we did here. 5 plus, for example, if I change it to 122, 2 tens, 1 100, okay? So now we're ready to do some practice. I'm going to erase this here. So, first we're going to try to do 2 in binary. This should be pretty easy, okay? So, we'll write down our zeros, and we'll just remember that this is 2 to the 0, this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4th. Or 1, 2, 4, 8, 16. Okay? So now, if we want to represent 2, okay? 2 to the 0, okay, that's 1. So first thing we're going to do is just look at our bases. If it's just a number like 2, for example, just go like that. Okay? So 0, 0, 0, 1, 0 is 2. Okay? Therefore, 1 is just 0, 0, 1. Because we have 2 to the 0th power plus 2 plus 0, 2 to the 1st plus 0, 2 to the 2nd. Do another example. Let's do 10. A number that isn't an exponential power of 2. So we know that 10 in binary, let's start at 2 to the 0. Okay. Rather, let's think about here. What 2 of these numbers would easily add to 10? Obviously 2 and 8. Okay? So if we know 2 and 8 are the numbers that are going to add to 10, then what we would do is 10 is going to be equal to, okay, let's start at 0, because we're not trying to find an odd number. You only use the 1 if you're trying to create an odd number, because remember that all 2 to any power will always create an even number. So the 1 is to create all the odd numbers. And we know that our number system is half even, half odd. obviously being 0 even, 1 odd, 2 even. Cool. So we're going to start at 0. Then we're going to have 1. Okay? Now we're going to have, we don't want another 0. Now we'll have a 1 here. 1, 0, 1, 0. There we go. Now, let's talk about something a little different. Prime numbers. Prime numbers are a fascinating aspect of mathematics because there is no pattern to them. Although I described the even numbers as 2n and the odd numbers as 2n plus 1, a method like that does not work for the prime numbers. I will remind everyone that a prime number is a number in which two smaller natural numbers, and I'll remind you all that a natural number, that's the natural number symbol, is equal to counting numbers. 0, 1, 2, 3, 4, 5. Okay? So, if I wanted to see if 4 was a prime number, can 4 be created by two smaller numbers being multiplied together? Obviously it can, because 2 times 2 is 4. So, we'll do another example of this. Okay, 0. 0 is kind of a weird one. We don't know if it's a prime number or not. I at least don't. I think it might be. I'm not sure. But let's think about 1 here, okay? Do any two smaller numbers than 1, so 0 is our only option here, can they be put together to create 1? No. The only thing that can create 1 is 1 times 1. Let's continue here. 2. Only thing that makes up 2 is 2 times 1. Same thing goes with 3. 3 times 1. 4, however, is not a prime number. 2 times 2. Likewise, 5 is a prime number. 6 is not. 7 is. 8 is not. 9 is not. 10 is not, but 11 is. So, now we're going to talk about a pseudocode example of a prime number calculator, okay? So, as I just described to you guys, we're basically using division here, okay? So, in the example of if 7 is a prime number, is 7 divided by so we're going to take 7 and we're going to divide it by all the numbers smaller than it. So 7 sixths, 7 fifths, 7 fourths, 7 thirds, 7 seconds, 7 firsts. Are any of these numbers 0? The answer is no. These are all numbers greater than 0. This one is almost 7. This one is about 3.5. This one is a little less than that. This one's 7 fourths, 7 fifths, 7 sixths, etc. So what we can say is that a prime number divided by any number smaller than it, the range of numbers smaller than it, if the remainder of that number, remember that the remainder here is 7, remainder here is 7 divided by 2, and obviously 7 divided by 1 wouldn't work because that would indicate that it is a prime number. So ignore that. All of these numbers are remainders, right? Because if we thought about, how many times does 3 go into 7, right? We'd say, 3 goes into 7 2 times, multiply this, subtract, and you'd get 1, right? That's why we could say 2, I think it'd be, we do 2 plus, ignore that. I don't know what's going on. Ignore that. But it's besides the point. We know that if we take 7 and divide it by any of the numbers smaller than it, we're looking for a remainder to be 0. A remainder that is 0 would indicate that it can be made up by two smaller numbers. So, to create this prime number calculator now, what we'll say is first, we need a user to choose their number. So we'd say input, right? Our input is going to be equal to the number, okay? Call it number for our cases. Now, we're going to create a logic statement, a for statement. So we're going to say for I in range, it doesn't matter what you use there. I in range of our number, of 1 to our number, non-inclusive, so we don't want to include 1, we don't want to include 1, we don't want to include our number, okay? And if, then we'd say for I in range, and then we'd say if our number, mod, the mod symbol is the percent symbol, modulus, basically saying what is the remainder. So it divides it and then it sees if there's a remainder, okay? If the modulus of our number divided by I is equal to 0, then number is composite. Else it's prime number. Okay? And let's test this here. Okay? So if we say our input number, we're going to say that this time this is going to be, let's call it 12. Okay? Now we're going to say for the I in the range of 1 to 12, non-inclusive. So obviously in programming it's kind of weird because it like cuts off the first, it's depending on your language, it can be kind of weird when dealing with ranges, but I'm using the mathematical case where neither 1 nor our number are included, so 1 and 12 won't be included, so we're going to be dividing 12 by 2, 12 by 3, 12 by 4, 12 by 5, etc. up to 11, okay? Then, so now we're going to be using the modulus operator. So now we're going to be saying 12 divided by 2, that's equal to 6, right? That mod 6, is there any remainder on 6? Is 6 a whole natural number? It is. So we immediately know our number is composite. Imagine we're doing a number like 11, for example. Changing all of these to 11 now, we'd see, okay, 11 by 2, we know that's not a whole number. If it was 12, it would have been a whole number, but it's not. Now we'd say, okay, what about 11 by 3? Also not a whole number. 11 by 4? Still not a whole number. There will be some decimal here, okay? Now say 11 divided by 5. Now say 11 divided by 6. 11 divided by 7 now, okay? So, we can see that all the numbers counting up to 11, so our final one would be obviously ... 11 divided by 10. And we can see that all of these numbers have a remainder of something other than 1. Remainder in this case, we'll take out my trusty calculator. The remainder in our first case is 0.5. In our second case, it's 2/3, and continuing on, right? So that's how we know that this number is prime, because none of these numbers have a modulus remainder of 0. So yeah, hope you guys enjoy. Have a good one.